Welcome to Unit 5, Lesson 9. We're talking about scaling the inputs right now. So this is where we left off before we were sent home for our time. When we think about inputs, we're thinking about our x's, our values that we have that we're putting into our equation. And because we're scaling inputs, or x's, this means we have horizontal shift, or squish, I should say, not shift. Horizontal squish and stretch going on. So if we have a graph that would normally be something like this, we can either stretch it wider. It's not going to stretch it taller. So this time it's going to keep our y-intercepts the same because it's not stretching it taller at all. So it could stretch it wider, or we could also see that we'll have some times where it's going to also be stretched, squished skinnier. All right. So we'll be seeing that just like all of our other input values, it's going to work opposite of what we tend to think. And so let's see what we have. Every weekend, Elena takes a walk along the straight road in front of her house for 2 miles, turns around, and comes back home. If we assume she walks at a constant speed, her graph would look something like this first one that we have here. So if we're looking at her distance from home on this walk that she takes, she starts with a distance of 0 from home. She walks 2 miles distant. She turns around and she comes right back home by the end of it. And the whole trip takes her 2 hours to do, and she goes a total distance of 4 miles. So she walks 2 miles, turns around, comes back, takes her 2 hours. So she's walking at a rate of 2 miles per hour. 2 miles here in 1 hour's time, and then 2 miles back home in another hour's time. We want to also think now this time with a function g that gives her distance in miles as she walks 4 miles per hour. So we've changed her rate, her speed. And that's oftentimes what we're going to see when we scale the inputs. Whatever is our x coordinate, we're going to be changing that input value. So she's walking the same distance, 4 miles, but we're changing how much time it takes her to walk the same distance. Notice that our vertical axis is still the same. So she's walking a total distance of 4 miles. This time, though, she can walk 4 miles per hour. So she'll leave home and arrive back home in 1 hour. And she has still walked a distance of 4 miles. So she's still going to be walking 2 miles to her turnaround spot and then 2 miles back. So her graph has gotten squished skinnier. So if we're thinking about how we're going to write this equation of g in terms of f, right? G means g of x is going to be by itself. I guess it's t. I always do that. Time. In terms of our f function of time. But we're making a change to our input. Now, if we're ever not sure about which way we're kind of looking at, we always want to use an input value that we have, because that input has to be the same in both situations. So here I'm going to say, hey, she walks that full 4 miles in 1 hour. So in our new function, g of 1 is when she has returned back home. I'm trying to scooch this down so you can see it a little better. There we go. So g of 1 is when she gets back home, and that matches up to, in our f function, I still need to keep the same t input, but here it's twice as long. And so we have a multiplier of 2, and so we'll see that in our new function, that g of t is f of 2t. So if we're thinking about where we were at 2 and where we ended up at 1, that's where this multiplier is coming from. Our t that we ended up at 1 is over here twice as long. So we had some important ideas here that when we see a change in our inputs, we're going to see a change in the speed that something happens, in the rate that something happens, in the slope of the graph, and we want to be able to explain that change, especially the change in the slope, is what's going to change that multiplier out in front. Okay, if we go back to the most basic y equals mx plus b, the equation of a line, if we increase that slope, that's increasing the input. See how it's a multiplier on x? That's changing our scale on x, on our inputs going on there. And b is what's going to move us up and down. Right? So what we really did here, when we think about the slope of this had a slope of 2 over 1. It rose 2 for every 1 hour. So this one had a slope of 2. Here, though, we went 2.5 an hour, which means if I'm scaling it for every 1 hour, or if we think about her rate, her slope is 4 miles for every 1 hour. So her slope here is 4. We doubled the slope, we doubled the input. All right, so that's another way that we can think about these scaling inputs. When we flip over to this new set of wheels, we've got this Ferris wheel happening, and we've seen Claire on a Ferris wheel earlier in this unit. And if we draw out our basic Ferris wheel that she starts with, this first one, she starts timing right up at the very tip top and is at a height of 212 feet off the ground. And we can see it takes her 80 seconds to arrive here at the bottom. So height of 0 at 80 seconds. And 40 seconds, she's at a height of 106. I'm just getting some values here from my table. Here at 20 seconds, she's at 181. At 60 seconds, she's at 31 feet. We have 2 different Ferris wheels we're looking at here. The first one ends up being twice the height and is rotating at the same speed. So her twice the height Ferris wheel is going to look something like this. And so all of these heights are going to be doubled, but because we haven't changed the speed, we're really just stretching this graph higher. We've stretched the height of this Ferris wheel up to 424 feet, and so that's where our new starting point is going to be. It still rotates at the same speed, so by the time she's down at the bottom here, it's going to take 80 seconds to get down to the bottom. So this time is also still going to match up. So at 80 seconds, she's still at a height of 0. Halfway between those two, she'll be at the halfway point in the halfway height. Right here, she'll be at 212 feet at 40 seconds. So this 40-second height just got stretched up here. It's still going to be happening at 40 seconds and is a height of 212. Now you might start seeing the pattern going on in the table. Math is all about patterns. Taking each of those outputs and multiplying it by 2, we're finding all of our new outputs for our graph. That's going to help me find out what these other values are. So we have a 62-foot height at 60 seconds and a 362-foot height at 20 seconds. So our second wheel, if we were to graph this, is simply looking at about twice the height. We've stretched, we're back to a vertical stretch going on. Our original wheel started at 212 and it dipped down to the bottom. And it's going to swing back up is what we're going to see, but here at the bottom it's hit 80 seconds. Our new wheel in blue is twice the height, and it hits the bottom at 80 seconds and is going to come back up. So we see that it has stretched everything, each of these points, taller. Now our second wheel is the same height as our original one here in red, but it rotates at half the speed. So instead of making it from this starting point at 0 seconds all the way around, or halfway around, in 80 seconds, it's only going to get a quarter of the way around in 80 seconds. So it's still starting at 212 feet. But instead of getting halfway at 80 seconds, it's only getting a quarter of the way because it's turning half the speed. So it's slower. It's not going to make as much distance in the same time. Notice that we're changing the rate that this is turning, or the speed of the wheel. So at 80 seconds, it is at a height of 106 feet. What we're doing is we're taking the inputs and we're kind of bumping them all down a row, right? So here at the halfway point between 212 and 106, halfway between 212 and 106, we know is this height of 181. And so for our new wheel, that's going to be half the height here between 0 and 80. So at 40 seconds, our newest wheel is at 181. It might be helpful for you to see a little color coding going on here, that at 20 seconds, our old height at 20 seconds is now our new height at 40 seconds. Our old height at 40 seconds is now our new height at 80 seconds. So we have taken the old input and we've multiplied it by 2 to get to our new output, or our new input of the same output. Let me say that again with this one. We've taken our old input, multiplied it by 2 to get to our new input with the same output that it was. So when I draw this new graph, I'm starting again at 212, but by 80 seconds, it still has a height here at halfway. It has stretched this graph. It's going to take 160 seconds for it to go hit the ground. It's going to take twice as long. We've stretched it wider. And so when we take this graph in red and we stretch it wider in black, that wider graph means that each of our inputs has been cut in half compared to what they used to be. To find our output at 40 seconds, we need the old output at 20 seconds. So if I look at these two equations, I want to think about this one because this is the one that we're talking about. This is our new idea. Our h of t graph that we have takes all of our current inputs, the newest ones that we're going for, and what I need is the value at half of the input previously. So my output here at h of t is the same output as half of t on the old one. So if I need 40, in my new one, I need to know my 20 of my old one. Our G function just took everything and made it twice as tall. All of those output values that we had, it just doubled every output. It stretched it twice as tall. This one made it twice as wide. And notice the difference in what that looks like, right? Here the graph stretched wider, but in order to do that, we had to cut our inputs in half. Here we stretched it taller. We could take our outputs and double them. Now we can't find these outputs for our newest wheel at 20 and 60 because in order to find h of 20, we need to know h of 10. And we don't know that, right? Because we need our half of our former input. To find 20, we need to know 10, and f of 10 in our original table is not known. It's not in there. We could estimate certainly between these two and know that it's somewhere between these two numbers, but I don't know what it is exactly because it doesn't tell me that information in the graph. In the same way, h of 60, we would need to know, oh, I'm sorry, that should be an f. We would need to know f of, let's see, half of that. We would need to know f of 30, and again, that's not something that's in our graph, in our table of values up here. We don't know how much we are, what our height is at 30 seconds, so I can't, with positivity, fill it out in our table here, so we don't have exact values for those. So a big idea that we have so far, if we have a multiplier out front, something that's doing horizontal change, if it's greater than 1, it's going to be taller. If it's less than 1, it's going to be shorter. I should say between 1 and 0. And remember that if A is negative, it's doing a top and bottom flip over the x-axis. So everything here is going taller and shorter and vertical flip. Everything here with our inputs, we tend to call it our C value. In this book, you'll see in some of the practice problems, they call it a K value. That's okay, right? We're just assigning some kind of a letter, some kind of a scalar multiplier. And we're going to find out that if it's greater than 1, it's going to make it skinnier. And like this one, if it's between 0 and 1, it's going to make it wider. And again, if it's negative, this is where we're going to be doing a flip left and right over the y-axis. So all of our x's turn negative. And all of our negative x's turn positive. That's kind of a nice summary right there. And that's also something we're going to keep in mind as we keep on doing some more of our multipliers here. Things that we're looking at as far as inputs and outputs. We're going to be looking at taking that multiplier and applying it to our original input to get our new output. We're going to see that coming up. But we should keep in mind that if we want something to be skinnier, we need to make sure that it's got a multiplier, a scalar that is greater than 1. If we want something to be wider, we should have something that's a decimal or a fraction. Let's look at the many transformations of a function p. It's going to take us through what I can see right away is a vertical stretch first, and then we're also going to start playing with some more horizontal changes. So our first equation is the solid one, p, and it asks us to write an equation for k in terms of p. We need to figure out what the multiplier is on the outputs. Notice it's got the same zeros of the graph where it's hitting the x-axis. So I know it has taken this and it has stretched it taller because these points are locked in. So it has taken this point at 2 and it has stretched it up to 6. So when I think of k at 1 equals, oh, that's our original one. P is our original equation. P at 1 equals 2. Our new equation, k at 1 equals 6. So I need a multiplier that takes those outputs. What do I need to multiply 2 by to get to 6? That multiplier is 3. So we're thinking about k of x being 3 times taller than p of x beginning. Taking an input-output pair or a coordinate pair like this and looking at what changes for our outputs tells us it goes 3 times taller. Our next one asks us on the same set of axes, graph the function m, where m of x is p of 0.75x. I think first that 0.75 is less than 1, and so because it is less than 1, our graph should be stretched wider on the inputs. So if I start looking for a graph, if I'm trying to apply this multiplier, and I'm applying it here, I need it to be wider, otherwise I'm doing it backwards. Okay, so use your brain first. What do you think it should be doing so we can make sure when we actually do it that we have it right. Okay. So if my old x input, I'm trying to find what my new value would equal. If my old one is hitting the graph here at 4, I need to think of what that new value of 4 is going to be. Right? So if I think about this as that 0.75, remember it's got to be the same inputs and outputs that we're doing. Our x's have to have the same value that we're looking at. So I have to figure out if I have an output at 4, that x is going to have to be the same over here. So the new 4 is 0.75 of what our new guy is. It's kind of counterintuitive. So I keep on kind of just taking some time to slow down and say, hey, really think about this in your brain. My number has to be bigger than 4 for it to stretch wider, and in this case it makes sense that if I'm trying to figure out what my x is, I should be dividing by 0.75 to get a larger x value. So my new number is 5.3 repeating. So it's taking this, what was at 4, and it's stretching it here to 5.3. What was happening at 1 is now happening, I'm thinking of this like 3/4, is now happening at 4/3. 1 and 1/3. So what was happening here is now happening over here at 1 and 1/3. Everything at the y-axis is locked in. Everything is stretching a little bit farther away from the y-axis. So our new graph is going to look like this. What was happening at -1 is now happening at -1.3. What was happening at -3 is now happening at -4. So there's our new graph in pink. Looks like it's giving us another equation, an n of x, and this one is 5 times the input. My scalar is greater than 1. I should have a skinnier graph. And one way to think about this is that it should be 1/5 as wide. 1/5 as wide. If we can make a comparison like this, maybe this is going to help you make more sense of those inputs and outputs that we have. So to find those new inputs that are matching up with our old ones, we need everything to be 1/5 as far. So all of our new x's is 1/5 our old x's. Right? So if it makes sense to you to kind of invert this to figure out what that multiplier is going to be, what that scalar is for our new and old, we can do that too. So our original, I'm going to keep on going back to these endpoints here. Our original point at 4 is now going to be 1/5 as wide, and so our new point is at 4/5. So this new point is happening here. Man, oh man, this is going to be a super skinny graph. What was happening at -4 is going to happen at -4/5 here. Again, our y-intercept is still the same, and our height is still the same. So between our origin and this new green dot we have here, we're going to have to go all the way up to 2 and back down. And all the way down to -2 and back up. Here is our new graph here in the middle. See how super squished it is? It's 1/5 as wide as our original black graph is here. Now it's going to ask us to throw even one more function on top of this. I'm going to use a different colored pen. If the point furthest to the right on the graph of P is 4, 0, which is what we've been working with, our endpoints up here. So if the point furthest to the right on the graph for a function q is 18, 0, write a possible function for q in terms of p. So 4, 0 becomes 18, 0. So even just one set of ordered pairs should be enough for us to figure out what this scalar is. Now it's stretching it wider. Okay, so I'm going to stop and think with my brain first. It's going wider of a graph, and that means our scalar should be less than 1 for it to go wider. To make something that is less than 1, I need to figure out, hey, what am I multiplying this 4 by to get to 18? Oops, other way around, because it's got to be less than 1. What am I multiplying 18 by to get to 4? Right. What am I multiplying 18 by to get to 4? So our old coordinate at 4 becomes our new coordinate at 18. And so we can look at it as 4/18. We could look at that also as 2/9, or if we were really inclined to put it into a decimal, 2 divided by 9 is 0.2 repeating. So it would have a 0.2 repeating multiplier. So to write an equation of what this is going to look like, remember this multiplier has to happen inside our input. So inside the parentheses, we'd have q of x equaling our original p function, 2/9 of x, or we could also write it as a decimal, something like that. That's our end of lesson 9.